It is a great pleasure and honor to introduce Wolfgang Eberhard. He's here for a couple of months. This is about the middle of his trip here, so he's going to be here for another 3 weeks. So you have more chance to talk with him after his talk, because you're going to find his talk to be a real treat. Wolfgang Eberhard got his PhD from at DAISY, working at DAISY. That was the early days of synchrotrons. And after completing his PhD, he came to US for about 12 years. At the beginning, he was a postdoc, and then later on became a professor at Pennsylvania University. He continued working at Brookhaven National Lab, and then he joined Exxon and had an industrial experience for another 6-7 years before coming back to Germany. So he did few assignments there, but notably he was the director of Bessie's synchrotron, which is pretty much the same as the advanced light source what is today. They kind of go hands in hand, they do upgrade and we do upgrade and same thing along that lines. And then in the later part, around 2010 or so, he also became the director of energy sciences or head of energy sciences for Germany research. Currently, he is is associated with the University of Hamburg, carry out research at DAISY. He is affiliated with Center for Free-Electron Laser there. Over the period of time, he has done a lot of research in different areas. He has published over 300 papers. His area of research is in angular photoemission, X-ray emission spectroscopy, looking at both the gas phase, clusters, and condensed matter systems. Some of the notable things which he has done are also for the basic energy sciences. He has been asked to be part and organize workshops and write a report, which is the science direction for basic energy sciences. And he's going to tell some of those along that line. But the most important is that what he picked up the topic is the most interesting and very hot topic. And you can see right over there that while free electron laser investment is there, why do we need the diffraction-limited light sources or synchrotron facilities? So without any delay, I like Wolfgang to have the maximum amount of time. So let's welcome Wolfgang Eberhard.
Well, thank you very much, Sahid. It's a great pleasure to be here and discuss with you these things. And I also see this as partially personal, biased by my personal views, but also as a matter of discussion. I put it up for discussion. But it's certainly of relevance also in a larger scheme and for the funding agencies, because synchrotron radiation has been a fantastic success story over the last decades. But about 15, 20 years ago, it somehow it branched out in two different branches. But while the backbone of the work has been done at synchrotrons or storage rings, new exciting possibilities came along by Linac-driven light sources like free-electron lasers. All of these facilities cost between several $100 million and more than $1 billion. And now the question arises slowly, well, do we really need both, or can we do it with, all with one? My firm position on that one is we really need both, because they're really complementary. And I hope at least I can convince you of that, what the relative merits of both of these machines are. And I want to take you back to about 2008. 7 years ago, there was a discussion going on here, and this was initiated by BSAC. There was a subcommittee installed, and then Franz Simser and I were put in charge to organize a photon workshop to look at the new science possibilities with the next generation light sources. This was just after all these various reports. This is a very very well received and very well written science aspect of it, and there's more machine aspects, and these highlighted. But now we were supposed to organize a workshop, and BSAC gave us a very strong charge and complicated. We were supposed to identify the connection between major research opportunities and the capabilities, find killer applications that could become the scientific drivers, emphasize energy-related and life sciences, consider the whole photon energy range from UV to X-rays. And this was the toughest one, at least in the committee. Do not choose a specific light source design. Consider only the photon attributes required for the most promising research, which was probably a wise statement by BSAC, because otherwise we would never have come to a conclusion what would be the case, but it also made the whole report a little bit complicated. And I also find it interesting that somehow I didn't see this as a charge. This is somehow a preempted statement of the report, that there should be strong coupling, but okay. What was the situation like then? As I said, the backbone was largely photon sources and storage rings, and you all know these parameters. I don't need to go very much about it. These are insertion device-based machines. The energy range is from terahertz to 100 kilovolts. Energy resolution is fantastic. They're all independently tunable. 50 simultaneous experiments, totally selectable polarization, and partially coherent radiation. And this is based upon the electron parameters in the ring, in the GeV range. This is something I come at the very end to. The energy spread in there is something like 0.1%. And the emittance, which is the size of the electron beam in the ring, is typically in the few nanometer radian regime. The lifetime of the electrons in the ring is much larger than the relaxation time of the electrons, so it samples, the electron beam samples all of phase space and fills it completely. Linac-driven FEL sources are totally different. At the time, the photon energy ranges considered were between 10 eV and 10 kilovolt, and they largely relied on the self-amplified spontaneous emission process for FEL radiation, which meant you had very spiky pulses, very little control of energy and time structure. The pulse length was 10 femtosecond, but varying. You had to do all the pulse characterization and characterize all the individual pulses. Spatially, they were coherent, but one experiment on the whole facility. The electron parameters that enabled this, the electron energy range, is somehow in the sub-GeV to GeV energy range, is that the emittance of the electron beam in the Linac goes down with energy, and it has a much smaller energy spread, and the bunch charge is about 1 nanocoulomb. The next stage was already on the horizon at that time. Seeded FELs to get rid of the SARSA process and have better pulse control, and you were superconducting Linac with many more pulses. This is the report. This is the outcome of one of the main messages, but it never got across. I must say this was an utter failure in that sense, that the photon attributes were put here, the various science areas here. It was meant to read that for this part of it, you need a ring source, and for this part of it, you need a Linac source. But this is simply not. But we had at least two conclusions in there. The science driver or killer attributes were femtosecond time resolution, which opens a new territory where atoms can be followed in real time, and the electronic transition is all matched at their intrinsic time scale, and sub-nanometer spatial resolution, which really opens the length scale where you have quantum confinement and you look into the heterogeneous samples and can characterize them and therefore look at the individual quantum effects, catalysis, and electron traps. What we would have liked to say but couldn't say is this maps largely onto an FEL, and this maps onto a diffraction-limited storage ring. Now I can say that, and I'll try to convince you of that. One thing that was, however, we try to get across there, the summary is, first of all, the science for the future generation is very compelling, and the source parameters needed for these, for that science are not covered by any single type of source. You do need both. Free electron lasers, storage rings, and for the ultimate time resolution at lower photon energies, also laser-based sources. Okay, since then, at the time there was just MAX 4 in the planning, or just had started. It has really, the design, accelerator design has matured to the extent that by now the electron emittance can be controlled through a new focusing scheme in a multiband acromet, which gives, and this is very well known here, orders of magnitude improvement in the average coherent flux. 2 to 3 orders of magnitude improvement, and this is really essential and opens up new things. Still, if you look at these light sources and an FEL, the pulses out of these sources are vastly different, and this also determines the science. The pulses that you have out of an FEL, if it's a SARSA FEL, it is this spiky structure, fairly little control, so it moves in energy. It has, every pulse has a different time structure. If you have a seated FEL, you can control that much better, and you manage to get then fully coherent pulses out of it. And with the superconducting LINAC, you can get about 100,000 pulses per second at 1 millijoule each. So that means 100 watt coherent flux. In a storage ring, the pulses have not millijoule, but a factor of 10 to the 6, roughly, less power, so they have nanojoule powers, but they'll come much closer, and rather than 500,000, you have about 100,000 pulses, you have 500 million pulses per second coming out of it. So if you look at the average coherent power, it is not so much different. So that means as soon as you start talking about having, for certain reasons, to attenuate the FEL beam, you might even be better off using one of these sources. So these different pulse properties clearly define different areas of science. And I'd like to go then in the following through this, but the bottom line, and also this is also my summary slide, is what does a diffraction-limited storage ring allow you to do? It allows you to take movies in the broadest sense of the term, which means is you can interrogate your sample, probe your sample consecutively many times, and really follow a process and really study the function. This can be images, this can be spectroscopical information. You're limited by single pulse time resolution, but you can get through integration, longer integration than ultimate sub-nanometer spatial resolution, and you can really look inside heterogeneous samples. You limit the fluctuations to the time or average over them as long as it takes you to get a good signal. And you are in a linear, non-perturbative response. What you do with an FEL is you can take single femtosecond snapshots. And this is also phrased under the scheme diffract before destroy, or hit your sample and run, or take your data as quick as you can. Which means is you get a single time correlated to an external stimulus status information, but you're limited there by the number of photons in a single pulse, which gives you a limited spatial and energy resolution. It is if you want to look at consecutive images that way, you have an ensemble-limited average development. You do get, on the positive side, femtosecond resolution. You can look at nonlinear processes, very dilute systems, and in general, it is some structural tool, but by that includes also electronic structure. And then following, I'd like to go through examples of this and try to illustrate this a little bit. This was one of the first very successful experiments on an FEL, showing that you really can do these images and meaningful reconstruct them by Henry Chapman. This is the sample. We pass one UV FEL pulse into it, record the diffraction picture, reconstruct it, get the sample and the original sample image back. If they shine a second pulse on it, the sample has been destroyed and it's gone. So this is, but you can get enough information out of a single pulse. You can even do this with double pulses on the femtosecond scheme. If you use an optical delay there, you can use double pulses imaging, but that is about it. This is one of the main themes of FEL physics that you find in almost any talk you listen to. But I find this is somewhat misleading. It goes back to the question of whether this galloping horse has really its four legs off the ground at some point while it's running along. And that was really the snapshot photography. If you really can do this with an FEL, after the first image that you take, the horse is dead. Or it has broken a leg, or something else. Yeah? So this is the thing you have to be aware of, and then you have to start with the second horse, and whether you ever find this type of image is a little bit questionable. So, in more scientific language, consecutive time-correlated snapshots at an FEL are only possible with new and replenished samples. With a diffraction-limited storage ring, you can take these images, but you might be somewhat limited in the time resolution by the time it takes you to acquire a decent image. You might have to integrate over several pulses, and then you don't have the same kind of time resolution. But you can take these movies. This is nonlinear processes. One example shown also at LCLS. Certainly the regime, this is pumping a rare gas atom, neon in this case, and then exciting or shining in the light here, which corresponds to a laser transition, and then measuring the amplification of the incoming light. This is physics which only can be done at an FEL. It's a great example of what can be done there. And so the marking here clearly is for an FEL. People talk about transferring this process or looking at this process for solids. And this is something in terms of resonant inelastic X-ray scattering. What I show here, this is from data that we published a while ago, showing the content of this resonant process in the X-ray emission signal as a function of the energy above the edge. So this is taken for crystalline silicon. The dotted curve shows the silicon L absorption edge. So here it starts absorbing. What is shown here as the circles is when you excite with a photon energy at these energies here, the coherent fraction of the light that you get back out changes with the energy, which has to do with the fact that the coherence is broken simply by electron-phonon scattering or other scattering events where you have another particle involved. So this coherent fraction in RICS in solids is never as high or as large as it is in atoms and molecules. what is shown here, the curve, these are the experimental data, what's shown here, the curve, this is the inverse of the electron-photon scattering time. So it matches pretty well this curve that we experimentally determined and shows the breaking of the coherence in this case is certainly limited by that, and this destroys the coherence. So far to whether you can extend these types of laser processes to solids or not, that remains to be seen. One thing that is clearly very dilute samples, you look at atomic mass-selected clusters, you can make them in a source, mass select them then as ionic particles, bring them into an action region, and then study photo emission of these particles there as a function of the number of atoms in the body. This is what you can produce here. These beams are very weak, and so they're almost transparent to the XFEL beam. But the question is clearly, what can we learn from this? And I just want to refer to one thing. For these small metal clusters, metal particles, very little is known about the structural information. And whatever is known about them is coming from about 3 eV wide photoelectron spectra of the valence band taking the lasers and comparing that with density functional calculations. And if you look at gold with relativistic effects, the theory has certain difficulties or challenges there to master. But you find also very interesting aspects there. What is there known and postulated so far is that you have very unique structures. All the particles up to 12 gold atoms are not three-dimensional but two-dimensional. They're planar structures. And then you find something as cute as this tetrahedral structure for 20 gold atoms. What you also find is that while gold as a solid is very inert, I mean, you have gold jewelry and you don't worry about it deteriorating, small gold particles are terrific catalysts. They have different chemical properties and everything like that. But it would be nice to really confirm the structure of these particles by some other means than this comparison. And core level photo emission certainly would be a great help because you can identify different binding sites. So for this planar cluster here, you have 3 equivalent atoms like this blue one here in the center. You have 3 atoms which are equivalent for the middle of the sides here, the red ones. And then you have 6 atoms in corner positions. So if you look at the binding energy spectrum and distribution of the core levels, you would expect to see 2 lines for these 3 atoms each and 1 doubly as strong for the corner positions. And that would give you a clear hint what's going on in the structure. Similarly, you can look at this tetrahedron and then make a similar assessment and get an additional hint on the structure of these particles. They also have very fascinating dynamics because what you have here is you pump these with a photon, which is a huge amount of energy that you put into a small particle, and then this energy cannot go anywhere. It stays localized in that small particle which has only very few degrees of freedom. So you get a lot of electron-electron scattering, very much energy transferred into the vibrational system, and it still stays localized in space. So you have even microseconds later, you have delayed evaporation or thermionic emission. You could also have very quick fragmentation. We've done part of this with femtosecond lasers, but again, it would be very interesting to look at this in chemisort clusters with an FEL in terms of getting more information about the structural changes, chemisorption position. There is, this is more than 20 years ago, a very interesting paper that came out teaching lasers to control molecules. And this is being done the idea about this is you have a molecule where you do some photophysics, you do an excitation to an excited state, and then with a time-correlated pulse, at the correct time, you can drive a chemical reaction, which is here schematically indicated, in a certain direction. This works with lasers. You can even have a learning algorithm and look for certain fragments that are coming out of it. And the system can identify that by itself and find the right pulse shape, which to use to hit this in the right sequence. But this is also something ideally to probe with a free electron laser, because the seeded FEL can deliver synchronized pulses with a controlled shape, and that way you can really enter into this. Now this is one of the holy grails, femtosecond nanocrystallography at the FEL. As I say, the first examples I give are largely to emphasize FEL physics, and the latter part will be diffraction-limited storage. So this is the achievement photosystem 1 in nanocrystals. It's a heroic effort, and you get something like 8.5 angstrom resolution than if you take the images and sort them over 10,000 nanocrystals. The actual catalytic centers, which are these red parts here, are not resolved in. And what is also said, what they also looked at is to look at the changes in the electron density with the length of the pulse. My remark concerning that is, this is makes it quite difficult, and the electron density has to change even faster than 10 femtoseconds, because proteins are largely consistent out of carbon atoms, and you can make a carbon 1s hole in the carbon shell. The lifetime of that is just about 10 femtoseconds. So within that time, you go from the first ionized state to a doubly ionized state, where you have 2 electrons missing out of the valence shell, and you should lose that charge, and they are removed fast. So that you have to keep that in mind. And the question is, how accurate can that be, and how much that limits the accuracy. If you look at another biological complex, this is the photosystem 2, where this famous Koch cycle was first formulated in the 1970s. This is again the structural transitions of the photoactive cluster that is responsible for the oxygen evolution, the water splitting in this biological molecule. This still keeps changing, even though the original process was formulated in 1970. The time scales change, and sometimes people even propagate additional states in there. People have learned, however, meanwhile, to prepare crystals of these proteins in these various states. And as far as I can tell, and I'm no biologist, but I had to put some biology in here, into this thought. The structure first came from Exaf's investigation, where the structure of that complex was first resolved and first shown in different states, also for doing this cycle. That was some of the key publications are mentioned here. Then came X-ray crystallography, which confirmed the X-ray structure. Now, beginning of this year, came another FEL study where they said, no, this is all slightly wrong. The distances are not correct. And the Exaf's study is also not giving the right distances within 0.2 angstrom limit. But you have to do it. You take a large crystal, take single pulses from an FEL, 10 femtoseconds, and then move the crystal each time it was hit by it. I think to me, it looks like this question is still open. How much radiation damage is in there, but how do we really can unravel the function? And the transitions in between, this will remain an active theme of research for quite a while. And the question whether we really should use these single FEL pulses, where even with, what I just said, within 10 femtoseconds you have changes going on in there, or a diffraction-limited storage ring where you do these state and time-dependent EXAFS measurements. Probably both will give some interesting answers, and you have to get the complete picture at a later time. Now I'm coming back to solid-state physics, and where the interesting theme is all the interaction of the different degrees of freedom, orbital spins, electronic charge, lattice vibrations. And the coupling between them leads to many different new phenomena. I mean, one of them is superconductivity, where you basically couple the charges and spins with a photon lattice to certain particles that can move them through unimpeded through a solid. And magnetic storage media, quantum computing, and lots of also technically relevant things arise from that. I switch to my own, or go to my own bias and look at magnetic systems a little bit to illustrate what can be done. And this means magnetization dynamics. We really also, since about 15 years, know now that in the femtosecond time scale we can switch and influence magnetic moments. And you want to go down to the nanometer size to change the bit patterns. So we have these bit pattern media. So what can we do and can learn about the initial pulse when you hit a laser, take a laser pulse and hit a magnetic medium, and then try to make it switch by that laser pulse. And this is something we did in the lab. This is done now with lasers. We have an infrared pulse coming onto a nickel film, and then probe it with a VUV pulse and look at the photon emission. And this is the electron distribution that you see out of there. And it's shown in an unusual plot that this is semi-logarithmic. But what that means in this representation, the Fermi function is actually a straight line. So whenever you can approach that distribution by a straight line, then you have something like a Fermi distribution, and the slope of that line gives you the electronic temperature. And so this answers immediately two different questions. First of all, what you have when you have both pulses in overlap, you definitely do not have a thermal distribution of the electrons. You cannot even describe the system by an electron temperature. And the electrons are definitely not at equilibrium with the lattice or the spin system. So this tells you, well, you need about maybe 200, probably more like 400 femtoseconds until you really have established something like a Fermi distribution of the electrons. You have a straight line here. Here it's shown for the 800 femtosecond. That means now your electron gas can be described by a temperature, but that is certainly elevated and different than the other temperatures of the sample. Then it can interact with the other degrees of freedom. Studies like this can and will for quite a while only be done with very fast femtosecond lasers or with an attenuated FEL. What is shown here is this is how, relative to the pulse width, the energy levels in the system change their energy. This could be collapse of the exchange splitting, but since there's only one level visible in these spectra, it's not really clear whether it is collapse. But it would be nice to have a broader access to it, and as I say, this would be possible with a laser source or an attenuated FEL because you need the femtosecond resolution. And then you see here then on the picosecond time scale, the temperature is defined, that's the blue scale. And you see also how the energy somewhat recovers of these states. So this would be the initial part of the demagnetization process. More of it you can then do with the synchrotron, where you look at magnetic moments, the scattering, dichroism. We've done the femtosecond slicing, and this is certainly something which you want to do with the diffraction-limited storage ring as soon as you come into that time regime. And this also gets me now to something, patterned magnetic media. This is one way of producing them. You take some spheres, nanospheres, and just evaporate your films on there. And then these films break up into patterns for fairly regular size depending by these spheres. These are the people that produced them originally. And if you now look at the, put these a film or a sample like this into a magnetic field, well, you see how the bits in this medium flip, and you see adjacent bits and how they influence each other as the magnetic field is cycled. And this is something you can only do with a diffraction-limited storage ring, because you want to take consecutive images, and then that way you can also look at domain wall motions, you can look at the famous skirmions and other things. So for this, look at magnetic media and processing these media. It's certainly not something you can do by an FEL. This is a very interesting study for magnetic scattering, which is also a little bit scary. It's a breakdown of the X-ray resonant magnetic scattering signal while you shine an FEL pulse on the magnetic medium. What is shown here as a difference, it's again this standard cobalt platinum film. Now magnetic scattering signal, that's this one here, at the cobalt 3p edge, cobalt n edge, at flash. And if you take an average over 1,000 pulses, where each of them has 7.5 millijoules per square centimeter, you get a decent magnetic scattering signal. If you take a single pulse, which has 5 joules per square centimeter, then you see very weak remnants of this magnetic scattering only. You get the scattering right assimilated here. You do not destroy the sample in this case, but the conclusion in this paper is what you actually do by this pulse is you start ionizing all the individual atoms in the sample. This is the case for 7.5 millijoule per square centimeter flux. This is the fraction of the neutral atoms in the sample, and these are the singly and doubly charged atoms in that sample. If you take the much stronger FEL pulse, you dynamically start to ionize all the atoms, and already after 10 femtoseconds, in this case, half of the atoms in the sample are ionized. Which means as the absorption edge shifts now, and you run out of the contrast window. So basically what that means is you don't have the dichroism signal anymore, and this is really limiting the ground state interrogation of your sample. So clearly for femtosecond resolution you need the FEL, but it's much more preferable to use the weaker pulses from a diffraction-limited storage ring. And I also want to point out the same process is also relevant for resonant inelastic X-ray scattering, because you want to look at the ground state of the sample, and you don't want to have all the atoms in there ionized and take a signal of that. So this is very disconcerting about the FEL process, and you might have to attenuate a lot. What is very interesting in the proposal also is to look at varying magnetic fields. And you can have pulsed fields. up to, in this case, up to 30 Tesla or even higher. You can have higher fields like 60, 80 Tesla in pulsed fields. For example, for high temperature superconductors to look at the breakup of the pairing, you would need 60 Teslas or more, but that would be very interesting and fascinating an experiment to do. It is an open question whether you really want to do that with the FEL pulse, which is 6 orders of magnitude stronger. You get no signal, but you might influence your sample. While with the diffraction-limited storage ring, the question is what accuracy, how much can you see with a single pulse? Or do you have to average over 10 pulses or so and then average over the magnetic field? But it is certainly something, these pulsed magnetic fields interrogating solid-state samples leave room for both an attenuated FEL and a diffraction-limited storage. I want to show you one example which clearly has to do with imaging. This is something that Schneider did. He started this here. This has to do with electromigration in microprocessors. This is a cross-section of an AMD microprocessor where a lamella is prepared by a fib ion beam. This is still functional, so you can flow also some currents through it. And if you flow currents through that structure, and this video I think will work. Yes. If you flow a current through that structure, you watch this area here, the current is flowing here, and all of a sudden you will see some voids forming there, here. Then they migrate here, and then the wire is broken. So this shows you the failure online. You can watch this, the failure in microprocessors through electromigration. And the interesting feature, this was done together with AMD, one of the main chip manufacturers. They noticed that the diffusion of these voids occurs at the top interface only, and never at the bottom interface. So they changed the manufacturing process to prevent that diffusion and block that diffusion. So it has direct implications. But this is certainly something which you can only do with a diffraction-limited storage. Last part of my talk I'd like to spend on energy. And certainly we are all concerned about the energy system. The drivers for a change are increasing population, increase or stable standard of living, in dependency on the various sources, partially foreign, and then pollution, global warming. This all calls for certainly that we change your energy system. I mean, we have by now about 7 billion people living here. In 1970, there were half as many living here. And since then, our energy consumption or demand for energy has also doubled. By 2050, we'll have 10 billion people living on this planet. And they all will, again, ask for more energy to have a decent standard of living. So what we have to come to, and this was easily said, it's much more easily said than done, you have to make fuels from sunlight rather than burning fossil fuels. You have to generate the electricity without generating CO2. And you want to certainly look a lot at the energy efficiency because there's a lot of savings to be done. In all of this, there's various technologies and a lot of technologies involved. Some are mature. Hydropower is quite mature, for example. Others, like the solar fuel generation, is much less mature. You need much more research and can have much larger impact. But one of the big fields of research certainly has to do with battery, because this new energy system will partially at least be based upon intermittent sources like wind and photovoltaics and solar energy, and you need to be able to store this energy, long-term, short-term. Also, if you want to do electric cars, it's amazing how many electric cars one sees here working. Germany is by far not as good as here, as it is here. But certainly the batteries charging, discharging, getting the capacity up is a big theme. And there's these energy frontier research centers here which have been initiated locally, and the DLS is quite involved in this. And certainly one of the major things is to characterize the electrode interface and really go through charging, discharging cycles. Photoemission is ambient pressure experience is certainly one of the tools of choice there, where you can look through the photon energy variation, value depth, and then have the spatial resolution to look at this system. This can only be done with a diffraction-limited storage rate, and will be certainly emphasized much more on that. Heterogeneous materials with the coherence, the coherent imaging, which is also called picography. I still can't get used to that word. Where you take basically a coherent beam image, record the image of your sample that way, you get a diffracted spectral pattern that way, and then you can transform it back to get the real space structure. To look at batteries here, charging, discharging cycle, and this shows, this little table shows how much the improvement in terms of the factor of 1,000 better, higher coherence will give between ALS and ALSU. Clearly a case for diffraction-limited storage, and you could never do this with an FEL. I want to spend 2 minutes on something that we are also interested in, which we are doing here with it as ALS, and that has to do with organic solar cells. Prototype systems of that have some kind of chromophore molecule, very often it's one of those cyanides. And they are mixed with an electron acceptor. Why do you do this? Initially, the photoabsorption happens in this molecule here, but this creates an electron-hole pair, and this has a very large tendency to recombine and not make it to the electrodes. So you want to do that, what you do in the silicon solar cell, you want to have some intrinsic kind of PN junction where you separate the carriers. This can be done by adding something which has a high electron affinity, so for example C60. That way, and these energetically enable this. We are interested in looking at the time dependence of that process, and also look at that as a function of the morphology of the system. We can prepare these films in different morphologies, so just simply let nature do the preparation. This happens by itself. This is the nice thing. If we take something like a 1-to-1 mixture between this phthalocyanine and C60, we get a fairly regular pattern. These are lean images of these mixtures of C60 crystallites and copper PC crystallites. Other people have done X-ray diffraction on it and really shown that this is fairly crystalline. If we change that mixing ratio to something where we have 10-to-1 mixing between the phthalocyanine, the photoreceptor, and very little C60, the dark grains are then grains of the copper PC, and the grain boundaries are covered by a thin layer of C60. They're decorated by this. This seems, as a solar cell material, seems to perform almost as well, and the electronic structure is very, very similar. The band offset between both systems, even though the morphology is totally different, band offset is almost the same. But the question is the timing and the charge transfer time the same? We've done this here together with Oliver Gesser and Henry Bloom. And if you look at the individual systems, the carbon-1s photon emission, with and without a laser pulse on it, time correlated. You see the carbon-1s level of C60, and the laser doesn't excite the C60, so nothing changes. You see the copper PC, the laser excites it, still nothing changes. We don't understand that totally yet. We have to work on that a little bit. This is part of the research. But if you look there here, this carbon-1s level of the C60 falls right in between this doublet structure here of the copper PC. And if we then now take the combined system and look at 200 picoseconds after the optical pump was on the system, then we see here, this is the green curve, that there this line, and this is the C60 line, is shifted in energy relative to the other lines, which shows, and we interpret this, then that this is an indication that the electron has arrived at the C60. And we can look at that as in a time-dependent fashion. We try to look at it at the onset. The onset is faster than the time resolution we can get here. So this would be something for an FEL experiment, but we can also look at the decay and look at the changes of the charge as it's transferred off the C60 again to the electrodes as a function of the morphology of these films. So this is clearly, if you look at another big aspect of energy research has to do with catalysis. This is in various reports. Also microscopy, you can image catalytic function, which means you need energy information, and this is here, sticks in picture on the catalyst under operation conditions. This is environmental sciences, how bacteria express certain inorganic materials. All of this you like to study with the highest possible spatial resolution. And this is certainly, again, something where you need the diffraction-limited solution, especially when it comes to beam and photon emission. And this is an estimate now what you can do with photon emission at an FEL, and how much space charge is actually limiting you in this type of experiments. The space charge, which means is the Coulomb interaction between all the emitted electrons in front of the sample before you can detect them in your analyzer, they cause a shift and a broadening of the structures. And it certainly depends on the number of electrons that are emitted, on their kinetic energy, on the pulse length, that means the time span over which they're emitted. It depends on the spot size, how spatially limited it is, and on the angular profile. And there's an empirical limit that typically, as long as you have 1,000 electrons per individual pulse, photon pulse emitted, this is certainly working out still. It always depends on how close in energy you want to look at. If you want to look at something like a millivolt resolution, even that might be too much. But the energy resolution enters into that. So what's shown here is now the space charge and rep rate limit, and what that translates to, and this is done an estimate by Karl Rosenhagen, who's done extensive studies with colleagues at the FEL. The space charge limits this process that you cannot use probably more than 10 to the 6 photons per pulse. This is a little bit a conservative estimate. From laser sources in the lab, I would say maybe 1 or 2 orders of magnitude more is possible, but you have to watch out. And then, if you have a time-of-flight detector, you're also limited, in this case, to 1 megahertz. So this puts a very severe limit what you can do with FELs. You have to really attenuate the 10 to the 12 photons per pulse by a factor of 10 to the 6 And if you then not take a time-of-flight detector, but take a continuous spectrometer, take a continuous detector, you're much better off with a diffraction-limited storage ring than with an FEL, unless, again, you need femtosecond time resolution. But for any other aspects, the diffraction-limited storage ring is really the sole choice for these kinds of studies involving photon emission. You also want to do bricks of catalysts, resonant inelastic X-ray scattering, then you don't have to worry about the space charges. Big advantage. But again, in this case, if you start thinking about it, there's various reasons why a diffraction-limited storage ring with multiplexing detection, as it's being built up here, is certainly the method of choice to do this. Multiplexing detection is something you wouldn't be able to do with an FEL because the incoming photon pulse is very narrow in photon energy. And you have to worry, and this is what I alluded to before, about being in a non-perturbative regime, that you don't perturb your sample by the incoming X-ray pulse.
Okay. Did he try to please everything?
Well, that's good. So I don't go into this. This is one example where a transition state has been identified. And I comment just very briefly on this. This is done with an FEL and X-ray emission spectroscopy, and a change in the spectra curves of CO and ruthenium after it has been pumped with a laser pulse. The spectra changes. And so what is the essence of this publication is there's actually, from the chemisorped state through the pulse of that laser, the system goes into a weakly chemisorped transition state before it goes into desorption. This was done 12 picoseconds later. And again, I would think this is more something which you can do when you tweak the temporal resolution with the diffraction-limited storage. This brings me now, as Sahid requested, almost to the end. So I want to show my summary. This is the slide as I had it before. What I'd like you to take home is, I'll make it a little bit simpler, is if you think in terms of science, for an FEL, it's great if you want to do single femtosecond snapshots. You diffract, you take your data before the sample is destroyed, hopefully. You have resolution in the femtosecond regime. You can do nonlinear processes, nonlinear mixing. You can look at very dilute systems. But it's basically a single event type of answer you get. For diffraction-limited storage ring, the big advantage is you can take movies, you can take consecutive interrogation of the same sample, and you can, that way you have access to the ultimate spatial resolution. You can look inside heterogeneity. So if you really want to follow up on processes and understand the function, this is certainly the source of choice. And the last thing is, will it come together again, the field? I don't know. There's various proposals how this might come together in the distant future. This by combining basically a linear accelerator with a ring-like configuration. This was proposed by Kulipanov, Gennady Kulipanov in the 1990s from Novosibirsk. Kwang-Jae Kim, who's well known here, had a similar proposal here. This has the advantage that you are not in the total, you are in the limit of the linear accelerator in terms of the emittance. You can combine that probably with the lattice nowadays with the higher order focusing. And you have the smaller energy spread. The smaller energy spread allows you to support longer undulators. because the energy spread in the electron beam limits the length of undulator that you can put into your storage ring at some point. So maybe this is coming together, maybe not. Maybe they will develop separately, but we definitely need both of them. And with this, I'd like to thank you for your attention, and I'd like to specifically thank these people, Roger, Zahid, Steve, and Janos, because we discussed some of this beforehand. Thank you very much.
So we have time for a few comments or questions.
So I'm going to try to capture what I took away from the talk. It seems like your focus is on perturbation and damage in samples. That's the big piece of in comparing these light sources. Perturbing the sample and damaging it. Second, that I think you mentioned but didn't go into, was stability of sources. And that's very important because many experiments require shot noise limited detection. We're getting to levels where we always require very stable sources, shot noise limited. And the third thing was this idea of tunability or broadband. You mentioned that with as opposed to RICs. So I would posit that those are three areas that you're saying we should examine. The perturbation or damage, the stability, and the tunability or broadbanding, because there are tunability issues with long undulated. So if I captured those are right, and those seem like they would have particular emphasis in fields like electronic structure measurements. You mentioned RICs, you mentioned photo emission. Those limits then affect those experiments maybe the most. But also the 3D tomographic imaging part. So I don't know. I'm just trying to summarize your talk in some sense as a takeaway message for me. And
Okay.
is that accurate?
It's accurate. I wouldn't phrase it maybe quite so negative for the FEL.
No, I didn't say negative on either side. I'm just saying if one was considering it, those are the considerations.
You can express it that way, and I said it, and I meant it. Okay, but I would say it in a way as to say that with the FEL, the advantage is you have femtosecond resolution, but you only can take one single shot. This is the one thing. You have 100 kilos, but you have to each time have a different sample, a new sample. Well,
stand back.
That is
it? No, but it's a question. It's a
but
fundamental problem.
well, yeah, I think, and this is not so discussed. There is it's positive and negative. I mean, if the essence is the same. If I say you can look at nonlinear processes with the FEL, that's a positive statement. If I say you're in a perturbative state of your sample, that's the same thing said negatively. Yeah. So, because you really perturb your sample and influence your sample by the FEL fault. And people have to be more aware of this. Roger's question is, does it mostly relate to electronic structure? I don't think so, because structural information by X-rays is based on electron density. You don't see the nuclei, so you see the electron density. If you're missing electrons, then maybe the density altogether is still accumulated in the same area. That it would be the positive statement, but you're missing something. You're missing these charges, and that means your structural information is also different.
Okay, let's move on to some other questions. Jeff.
So, Wolfgang, this, especially like one of the last examples you showed, talking about some process that was kind of, I think, 10 picosecond time scale, and you said this is a great example for the DLSR. But could you amplify a little more how you do that kind of time resolution with 100 picosecond timescale pulses? That's one question. Secondly, with the very high repetition rate of only few nanoseconds for recovery time, how limiting is that in terms of what phenomena you can look at from your point of view?
Both of these things you have to take into account. Maybe I wasn't totally forthright that in a diffraction-limited storage rings the pulses are even a little bit longer than in a normal storage ring.
Right.
But you possibly can run it also in a certain mode where you get down to this 10 picoseconds.
Uh-huh.
I was just thinking about this experiment that if you are in this time regime, then it becomes interesting to look at it in a way where you're really sure that you probe the ground state of the sample by the X-ray pulse. And you're not having other influences in there due to the X-ray pulse.
I'm curious why maybe you said I came on maybe a minute or two late. You didn't say anything about this high repetition rate FEL schemes.
No, this is the high repetition FEL scheme. I took already the positives of them. The FEL I was considering on inherently, the experiments are the low rep rate, but I was always keeping in mind the high rep rate FEL. Based on the superconducting LINAC and having 10 to the 5 pulses. That's the high rep.
So let's move on to another question. Oliver.
It's less a question than rather a comment I would like to make, since this came up repeatedly. So I would also soften the statement a little bit that with an FEL you always need a new sample after every shot. That I think in part is due to maybe also a bit of a cultural issue of laser people. If they have a laser that gives out 10 to the 12 photons, they like to shoot 10 to the 12 photons on their sample. But you don't necessarily have to, and especially if you have a 100 kilohertz FEL, and you turn it down to as your example, 10 to 6 photons per pulse, for example. You can run beautiful photon emission experiments, for example, at very good data acquisition.
But this gets us into the number.
All right. Let's
No. Okay. If you turn down the FEL by a factor of 10 to the 6, the average coherent power out of the diffraction-limited synchrotron is going to be a factor of 10 to the 4 higher than this FEL.
Right, but you don't get 10 second resolution.
Yeah, that is. I always maintain that. If you need the femtoseconds, there's no choice but to bite the bullet, tune it down, attenuate it until you are sure that you get the signal that.
Wait a minute, if you have 10 to the 4, you can do slicing.
I know about slicing.
There's a lot of good experiments.
So we are getting
It
near
was
to the
successful
end.
but painful.
And continuation of this effort, I like to ask you one question, which is related with how much does it cost to do an experiment? Okay, so in a synchrotron, we know how many users we have, and we know how many experiments get done, because you pointed out, 40, 50 beam lines, and there's that many experiments to do. On the average, we know that with an FEL, as far as the early stages of FEL, which are currently there, it takes about $1 to $2 million of effort to deliver an experiment which is a successful experiment. On the synchrotron, we understand that this is probably less than 100K or so. Okay? The question comes out that the experiment better be worth that much more for the FEL. And I truly believe that in the case of a photo mission, there are better ways to do the experiment. Maybe there are certain class of high energy photo mission experiment. Those will be the only one, but most of the photo mission experiment you could do other ways, not FEL. So there was one question, who was raising the question?
I think this is a dangerous argument.
What about the
Because
dangerous? But that's a fact.
How much is the Higgs boson?
That's why I said
But you need, we need a Higgs boson experiment. What's the equivalent?
Okay,
Well,
let's
in
ask the
solid
last
state
question.
physics, there's too many opinions what the equivalent might be.
Yes, please.
One question, and probably goes a little bit beyond what you were talking, and I'm definitely on board with all the X-rays. But when you talk about microscopy, sub-nanometer resolution, and one of the examples was an environmental study. Electron microscopies are also pretty good doing this, both in the environmental as well as already in an X-ray regime. So how would you see the competition coming from that side, and how would that fold into what you're proposing here? So what is the competition? Because I mean, electron microscope might be a little cheaper. Again, I don't want to raise that argument, but in terms of science, I think in the end the scientists, I mean, they want to get the science done.
I think electron microscopy is definitely an alternative for it, and you have to see which one is better suited for the question you want to address. There's no simple answer to it.
Okay, with this one, let's thank Wolfgang.